There it is. Okay. All right. So today we're going to jump around a bit between three different chapters, 8, 9, and 12. These are chapters that have some information in there for you to know. Not all of it, but they're just little things in here that you should pick up on because the SPI is focused on the very big concepts, but in between the very big concepts, it has to sort of fill in some of those gaps with random questions, right? And we know that every exam does that. Every exam will ask you about particular things, and then it kind of just throws in a couple of extra little things here and there that are usually easy if you remember them. They tend to be definitions. They tend to be some rules. Give me a second. My cat wants to get out. Give me 1 second. All right. She had all the time in the world to get out, but she wanted to get out now. Okay. So, uh, these chapters 8, 9, and 12. Well, 12 is transducers, so that's transducers you have to know. But 8 and 9, it's just little things that I want you to pick up on. So we'll start in chapter 8. And I'm just going to run through the things that I feel you should know. I'll explain them very briefly. Just information for you to know. That's it. All right. So in chapter 8, they begin the chapter with a couple of definitions. Then they tell you the different parts of the transducer, the backing material, the PCT, and the matching layer. Those are really the important ones to know. Hence why the book then begins explaining them. They talk about the matching layer, the backing material, and then the PCT. All right, so the last time we spoke about impedance and how different tissues have different impedances. So some tissues may have a high impedance, other tissues may have a low impedance, and that affects how much of the wave goes through and how much of the wave gets reflected back. And that's every single tissue. As the wave propagates and moves through the body, it's hitting all these different tissues, and every single different tissue has a different impedance. And that's how your wave starts maybe reflecting more for some, reflecting less for others. Then that adds to attenuation. So it's a whole process that happens. And if you remember, I said that high impedance equals a high reflection. And if we just look at, things being in balance, a high reflection would be a low transmission. And this is what we spoke about on Wednesday, because there's always a balance, right? You cannot have high reflection and high transmission, right? It won't work. It's either a lot of you is coming back or a lot of you is going through, and I brought up the example about 10 friends going to a club. 10 friends show up to a club, 8 of them go in, 2 of them should be sent back, right? Because 8 going in plus 2 being sent back is 10 friends going to the club together. But if you have 10 friends going in and 10 friends being sent back home, I'm going to ask you, who are these strangers, right? Like, where did you pick up 10 other strangers that you had no idea were there, right? So it's always a balance. So with high impedance comes high reflection and low transmission, which means that a lot of it gets sent back, not a lot of it goes through. And in ultrasound, as I've been saying, everything is about going through, reflecting, going through, reflecting. If something doesn't go through, it doesn't see what's on the other side. So if you have a bone and you have a wave that hits it, and this wave, everything gets reflected back and absorbed and nothing goes through, then you cannot see what's back here. So then the machine says, oh, there's nothing back there, and it makes it a shadow, it makes it black. And I remember I said, don't go by that, right? Because just because you can't see something doesn't mean there's nothing there, okay? So why am I bringing back impedance? It's because of the matching layer. So you have your PZT, which is your element. You have your matching layer. You have your gel, and then you have your skin. All right. And the goal of this is where the wave originates at the PZT. The PZT vibrates, and that's the wave, a mechanical longitudinal wave that is being sent out. Now the journey here is this wave right from here needs to get all the way over here. And once it gets into the skin, then it travels through all the tissues. Okay. And then, okay, once it's within all the tissues, that's when you start seeing reflections, and that's when your image starts being created. But first, it has to make it there. And look at this journey. The PZT is on the far left, the skin is on the far right. Okay. And the problem with the PZT and the skin is that their impedances are very different. The book says that the impedance of the PZT is 20 times the impedance of the skin. So it's a high impedance. And a high impedance means a high reflection and low transmission. In layman's terms, it means that if I remove these guys and I put my element next to my skin, nothing will go through. Okay, because the transmission is low. The reflection is high, the transmission is low. It's sort of like a wave goes out and it just bounces back. And it's never able to go into the skin because of the big difference between the PZT element and your skin. Okay, so it's just being bounced back, never goes through. All right, so that's why we have this matching layer and the gel. So what is the matching layer? The matching layer is that part of the transducer that is this color. That is the matching layer. So it's the part of the transducer that actually touches the skin. You know, the part that we always wipe clean, that's the matching layer. That little pinkish, reddish surface. That is the matching layer, okay? So the matching layer touches the skin. And I don't know if you've ever tried this before, but if you ever grab that transducer with the matching layer and you press it really hard against the skin, you see nothing. Okay, you see nothing because you're missing this guy, the gel. All right. So this is how all of this works. We're trying to build a bridge between the PZT being very high impedance and the skin being that low of an impedance. We're trying to build this bridge so that the wave can travel and make it to the skin. And once it makes it to the skin, it does its own thing. All right, now we're good. Now it can start showing us what's there. But first it has to make it there. So the matching layer in the gel, in my mind, all right, this is the way I explain it, in order for it to kind of just make sense. Um, the matching layer and the gel are part of that bridge. And what they're doing is they're trying to close the gap, because that's pretty much what a bridge does, right? So if you have a step right here and a step all the way over here, and I ask you to jump to the other side, you're going to be like, what? Who do you think I am, Michael Jordan? Right? I can't jump that big gap. You have to put little steps in between for me to step onto the next and the next and the next. I can give you a little decent hop, you know, but not this big of a leap. That's a leap of faith right there, if I've ever seen one, right? So, um, what was I? So the matching layer tries to close that gap. And for me, again, this is how I see it. The matching layer says, hey, listen, PZT, you're a 20 and you're trying to get to 1. All right. I'll try to be like a 13. All right. So now the wave travels from a 20 to a 13, which, don't get me wrong, it's still a gap, but it's a much smaller gap than 20 all the way to 1. And then the gel comes in. And the gel says, all right, I'm in between the matching layer and the skin, because where do we put the gel? On top of the matching layer, right on top of that reddish surface. That's where we put the gel. At least that's where I do. I don't put it on the patient. I scan echo, so like for echo, we always put on the transducer. But I remember when I used to scan OB in the program, I would put it on the belly. I wouldn't put it on the transducer. I'm not sure why now that I think about it. But for echo, we put it on the transducer. That's I don't that's the way that I've always been taught, and it kind of makes sense because the position of the patient is a little bit different. So then the gel says, all right, I'm in between the matching layer and the skin. So if the matching layer is a 13 hypothetically, and the skin is a 1, let me close that gap and let me be a 6. So now the wave went from a 20, traveled to a 13, was running around in a 13, traveled to a 6, and now to a 6, to a 1, and now finally is at the skin. So all we did was we build this bridge for the wave to travel to actually make it to the skin so we can actually have an image. All right, so that is the purpose of the matching layer. And because of that, the way we clean the matching layer is specific. We don't sterilize it, we disinfect it. Because sterilization, and we'll talk about that in other chapters, sterilization can damage that. And if it damages that, it damages the bridge. And now waves may not be able to make it to the other side. And then your transducer is then done for. And I think it's like $10,000, $15,000 to replace it. So it's very expensive. So what is the reason that you can take the matching layer and dig it into a patient's belly and still not see anything? Because the gel is missing. And why is gel so important? It gets rid of the air. So the air is, whenever you press something against the skin with the transducer, there's air trapped in between. Like little air, we can't see air, right? So you think you're pressing and there's nothing in between, but there's air in between. And air um, scatters ultrasound, meaning it doesn't allow it to go through, which is why if you ever scan abdomen, you cannot scan intestines because they're gassy, especially if the patient is gassy. If they're not gassy, cool. But if they're gassy, as soon as that wave hits the air, it just scatters it. So it completely kills the ultrasound wave. Fun fact, if you ever scan animal ultrasound, as I did for about 2 months, I believe, we scan, well, I can't say we scan because I don't do it, but when we did the study for the abdomen, we scanned the intestines and we had to like map it out. Not entirely, but certain parts of the intestines. That's part of the study to actually map it out. And I guess dogs or cats are not as gassy, I guess, because when I did it, it was, you can see like meat, you can see like, oh, this is the colon, this is the pieces of the small intestines. You'll see some gas here and there, uh, you know, but we do it. I'm not sure. I guess they're not as gassy as 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 we are. All right. So that is the matching layer, the importance of it. So just understand that where it falls on this sequence, PZT, matching layer, gel, and skin, and just have that concept of mind that it just tries to build this bridge to get the ultrasound wave to the skin. That's pretty much it. There's something else to know about the matching layer and the element, which is the PZT. So it's about their thickness. The matching layer, and this is a very easy question on the SPI, is a quarter thick, the wavelength, okay, of the speed in the matching layer, okay? But the big thing to remember is that it's a quarter thick. It's a quarter thick because the PZT, it's half thick, the wavelength of the propagation speed in the PZT, okay? So don't get these two numbers confused. And my clever way of helping you remember what belongs to what is do this. So my Z looks like a 2, okay? And then you can read it as 1/2 right there, 1/2, and that's your PZT. And once you know that that's your PZT, that your PZT is 1/2, you know that the other guy is the other number. Okay, so that's my clever way of trying to remember it. The other thing is the backing material. Okay, and the backing material is actually quite important. You have backing material. And it's not really about knowing exactly like where this is and yada yada. It's more about these little consequences of having a backing material. Okay, that's more like what they want to know, what they want you to know. And this is just definition sort of deal. You don't have to go into depth understanding more about this. Just know that what a backing material is, and then the three little consequences of having a backing material, and your questions will really just fall under that. So you have a PCT element, and right behind it, you have the backing material. And what the backing material does is that it absorbs the vibration of the PCT. So the PCT vibrates, creates this continuous wave. Okay, when it vibrates, it creates this continuous wave, and the backing material chops it up. Okay, it chops it up and is no longer continuous. It now becomes a pulse. So backing material is for post ultrasound. So only post wave ultrasound uses backing material. Imaging is created by post ultrasound. So your 2D image, not just your post wave, when you take the waveforms, but your actual 2D physical image that you see is created by post echo. That's what they call it. There's a chapter called post echo. I feel like I'm talking fast. I'm sorry. I don't know what's. what's I had Chipotle earlier. Maybe that's like in my system right now. Let me take a deep breath. All right. Backing material. Okay. So the backing material belongs to the pulse wave, right? Not the continuous wave. And if you want to think about backing material, think about that little bell that you ring when you stay at a hotel in the front desk, that you ding it and it goes bling. And if you let that thing ring, it just rings on that one ding. It just rings and rings until eventually it fades out. Okay. So if you wanted to stop this, you could put your hand over it or anything over it, right? But you can put your hand over it. That's typically the tradition. So you ding it, bling. You put your hand over it, bling, and it stops. And then you can ding it again, bling, and it stops. Bling, bling. And at that point, you start getting a pulse if you continue to do that. Bling, 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 bling. That's a pulse, right? So that's basically what the backing material is doing. It's creating these pulses by absorbing the sound and then chopping it up. All right. So these three consequences for you to know are the following. This has decreased sensitivity. Actually, I write it differently. Has a wide bandwidth, a decreased sensitivity, and a low quality factor, a Q factor. And there's a formula for quality factor. It's about the main frequency divided by the bandwidth. You don't have to, honestly, you don't have to know that. These three things are more important than knowing the formula for quality factor. Okay, like this will get you through more questions than knowing that other formula. So now it's about knowing what these things mean. A wide bandwidth simply means many frequencies. That's what a wide bandwidth means, many frequencies. And remember what I said earlier about post echo. So whenever, let's say you grab a curved linear transducer and you start scanning, and you notice that the patient is a little bit on the heavy side. So you decide to turn down your frequency. You go to your machine, you select, penetration, or if you actually have the frequency numbers, you just lower it down. And just like that, you change the frequency of the transducer. Okay. Well, this is why. If you only had one frequency to choose from, how could you change the frequency? All right. You wouldn't be able to. So the fact that you're able to change the frequency on that transducer means that you have different frequencies to choose from. And if you ever look at the side face of a transducer, normally there's something printed on there. And it's the range of frequencies. So your transducer, for instance, a curved linear, I believe it goes up to like 10 down to 5, meaning that it can go as high as 10 megahertz or as low as 5 megahertz and everything in between. Those are many frequencies. And you can choose between that. Okay. So anything that's imaging has many frequencies to choose from. That's a wide bandwidth. Decreased sensitivity. So by having this backing material, it absorbs the vibrations. And when you do that, something always goes by the wayside. You're always going to lose something. And it also happens with reflections. When reflections come back from the body into the transducer, they also get absorbed by the backing material. And when that happens, really weak reflections never make it out. It's like the cemetery for weak reflections. Just like the spleen is the cemetery for red blood cells, FYI, because we always wonder, what does the spleen do? That's where red blood cells go and die. All right, so the backing material, because it's going to absorb and unfortunately absorb certain weak reflections that never make it out, every reflection is a piece of information. Every reflection. So if something doesn't make it out, that's information that you lost. Okay. Now it's not like the biggest of deals, because look, we're doing fine with ultrasound, right? But that is why they call it decreased sensitivity. And when it comes to waveforms, if you look at a pulse wave versus a continuous wave, a pulse wave normally will always be like this. A continuous wave normally would always be like this. So one has a window, a spectral window is what we call it. The other one doesn't. Okay, and we can put this on one vessel in the exact same place for both. Okay, in the exact same place for both, and you'll get completely different waveforms, the look of them. Okay, and it's because of that. It's because the pulse wave is not as sensitive. So there are some things that it's not going to see, or it's not going to pick up on. And then the continuous wave, which is the opposite, is going to see a lot. But we'll get into that in some other chapter where they compare this again. Okay, continuous wave just sees more, and that's like a whole conversation about sensitivity, which is really important. And again, we'll talk about it later. So anyway, you have a decreased sensitivity. That's what you need to know. And because you have a decreased sensitivity, the way I like to connect it to the low quality factor without using that formula, because I don't think it's useful to remember it for the exam, personally speaking. Deep breath. Decreased sensitivity, this is the way I think about it. If there is a low quality factor, when I think of the word quality and I think high quality, I expect perfection. I expect something to be flawless if I think it's high quality. If I think low quality, then I'm thinking, all right, well, I'm settling, right? There's something that's not really going to work as perfectly as it should, just going by the term low quality. So if I have decreased sensitivity, and that means that I'm going to miss out on some information, then this must be low quality. Otherwise, if it was high sensitivity, meaning that I saw everything, then that could be high quality because I see everything. Okay, so that is how I connect and remember that if I have decreased sensitivity, it means that I have a low quality. Okay.
Can I ask a question?
Yeah.
So if you would have high sensitivity, would that mean that you wouldn't have the backing material?
Correct.
Okay.
Yeah. So in some other chapter, it's like in the Doppler chapter, they bring this back and they compare pulse wave with continuous wave, and backing material is in there. but then they focus on continuous wave. So then I'll compare the two, and I'll pretty much just show you that if you know one, just flip it and you know the other. So for continuous wave, very easily, you could just do this. No backing material, and then flip each one. Narrow bandwidth, increased sensitivity, high quality factor. And there's your continuous wave. All you do is you just flip it. Okay. But again, I'll discuss it in chapter 19. All right, so that's backing material. Then some little things to know for you to read honestly. Read about the Curry point. Just know what the Curry point is, which is just a temperature, which that you don't want to reach. And then the sterilization versus disinfection. Disinfection is what we use because disinfection does not damage the matching layer. Because it's very important that we don't damage the matching layer. Okay, so disinfection is what we use, not sterilization. Just again, something for you to know and just pick up on, nothing else. All right. Now, the end of chapter 8 ties in a little bit with chapter 9, which starts talking about the like where the focal point is placed. Okay, so before I get into that, let me discuss the regions of the wave. So when you have a PZT, the PZT creates this beam shape. Okay, that is the beam shape. All right, this right here is distance, because if I flip this, I get this. Okay, and then if I just do this, well, there's my image. Okay, and what is all of this? This is depth, imaging depth, which is distance. All right, so just because it looks a little different, it's sideways, and it doesn't look like they're not putting a body on there, so you don't think that it's going into the body. Okay, so try to forget about that, and just know that this is going into the body. We don't see it like that on our machine, right? Like whenever we scan, we don't see a beam shape like that. We see whatever shape our transducer creates, right? This is what we see. But the ultrasound waves are creating this hourglass shape that you see here, okay? And this hourglass shape is going into the body. So all of this is distance. Now this distance, this shape can be divided into different sections, okay? The very, very center is your focus. And your focus is surrounded by the focal zone. It's a zone, right? So it's an area. But the focus is a single point, okay? It's a single point. It's kind of like when you focus your eyes on the single point. That's all it is. So then you have your focus, which is the very, very center. That is the center of the universe per se, okay? And then you have the focal zone, which is an area surrounding the focus. And the center of the focal zone is the focus. So again, the focus is just the center. That's it. It's the center. Now, the importance of the focal zone, the focal point, excuse me, is that it divides the wave. This beam shape, it divides it into this side and this side. Okay, this side is the near field, and as properly named, the far field. Now there are synonyms for this. The Fresnel zone versus the Fraunhofer, I think it's spelled Fraunhofer zone. So there are synonyms to them, okay? Kind of something to remember, all right? Because they could easily just throw in these words instead. So there you have the near field and there you have the far field. Remember that the focus is the center. The focus is the single point where the near field ends. And in that very same place, the far field begins. Okay. And that's very philosophical, in my opinion, because every time something ends, something else begins. Every time. Okay. If you're going through a lot in your life right now, the moment that that ends, something else begins. Whether, and that something else doesn't have to be something spectacular. Like, oh man, I just said, oh, I won the lotto, and I remember, oh, I gotta play the lotto tonight. So for for all of you listening, the Mega Millions is like really high right now. So go out and play, because I know I'm gonna play it after the call. Anyway, so if you're going through something in your life and the moment that ends, and let's say that now your normal life begins, well, something ended and something began. It happens every single time for with everything you do. Okay. So this is no different. So at this very point right here, my near field, uh, I'm not sure if I will come back if I win. So at this very single point where the near field ends, the far field begins. At this very single point. When I was in high school, I was a criminal justice major in high school because I went to a technical school that, you know, they teach you a career. And there's a very, very cool phrase in criminal justice which says, your freedom ends where my nose begins. You know, it's really cool because that is true. Like your freedom does stop where yeah, yeah. Sorry, I'm just reading a message. So your freedom does stop where my nose begins, because the moment that you cross that line and touch me, that's it. I can do something about it, right? It's no longer your freedom, right? You cross that boundary. So same thing here. Anyway, all right. So what kind of questions will you get about this? Well, they can ask you about what is this region called? What is that region called? And by the way, there's a region like right here called the dead zone. Okay. The dead zone is the region where you don't see anything. So whenever you're scanning, you notice that you see like tissue, 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 and then you finally start seeing what you're seeing. Like you see, you know, it's always in the beginning. That is the dead zone. You cannot see anything there. That's why it's called the dead zone. It's too close to the transducer for it to make out what is there. Okay, so they call it a dead zone. All right. So what kind of questions would they ask you? The name of the regions, that's one. But if they want to get into a little bit of math, which is very simple math, okay? So don't freak out. It's very simple math. What they can do is they can give you a few numbers in here. Okay, and I know in some of the review questions or in the book, you know, they definitely discuss this because they're trying to do a chapter review. So they have to ask you everything about the chapter. So they'll tell you that your near field, let's say it's 8 centimeters long. And they'll tell you that the width of your crystal is 6 millimeters wide. These are the only two numbers they can give you, or that they will give you. And then from here, they want to know, where is your focus? Okay, they want to know what is your diameter at the focus, like how wide are you at the focus, and then they want to know, when will your diameter be 6 millimeters again. Okay, so they can ask you these three questions. All right, and they can also ask you about the focal zone. The focal zone, where does it start and where does it end? So they can ask you that. And I'll run through these very quickly, because I don't think it's a big part, but it can get you a few extra points, you know? And considering that you will have the recording, even if I run through it quickly, you can go back and work it out, you know, and try to make sense of it. All right, so here are the rules. My near field is 8 centimeters, okay? 8 centimeters long. So 1, 2, 3, 4, 5, 6, 7, 8. Because it's going to my near field. Where does it end? At the focus. And here's the focus. So right there, it's going to be 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So if they ask you where's the focus is at the end of the near field. And what is the end of my near field? 8 centimeters. Now, 8 centimeters is my total length. Absolutely. 8 centimeters is my total length. But if I ask you, go to the end part of my near field, you're going to go to the length where it stops, and that's going to be 8. Okay, so that is where my focus is, at the end of my near field. So my location of the focus is 8 centimeters. Then they can ask you, what is the diameter at the focus? So you started off with 6 millimeters. And here's the trick. Anytime they talk about diameter of the crystal, it will always be in millimeters because it's small. And when they talk about the length of the beam, it would always be in centimeters because it's bigger. And when you scan, you always know that it's in centimeters, like in real life. It's always centimeters, 10 centimeters, 5 centimeters, so on and so forth. So if you get a question about this and some of the questions ask you about the diameter and they have centimeters in there, eliminate them, right? Because we're not talking about centimeters for the crystal. We're talking about millimeters. So that's an easy way to maybe get rid of a few choices, at least just one. So what is my diameter at the focus? The rule is, notice how your beam starts to taper and starts to become narrow. Okay, it's starting out at 6 millimeters wide and it slowly becomes narrow. So whatever it is at the focus is going to be less than 6 millimeters, right? There's no way that it can be 6 millimeters if I'm showing it to you getting smaller. The question is, well, how much is it? Like, what is that number? The focus is the most narrow part of your beam. Okay, that is where it gets the most narrow. Not a little bit after, not a little bit before. That single point is the most narrow. So remember that, because on Monday, I believe, yep, we're going to do elevational and lateral resolution. Okay, and that's going to come back. So the rule is, at the focus, your diameter is half of what it was when it started. That's it. Just cut it in half. So if I was 6, at my focus, I cut 6 in half. I am 3 millimeters. That's it. You just cut it in half. Whatever it was when it started, cut it in half. Okay, that's it. Nothing else. This is why they can ask you these questions and still not feel like it's math, right? Because they can just tell you, hey, cut something in half. And you're not going to be there like, oh, where's my calculator? Oh my God, is it getting hot in here? It's like, no, just cut it in half, right? Something that we can all do. And they're not going to give you crazy numbers either. Like 131. It's like, oh, what's half of 131? Oh my God. No, simple numbers, all right? Simple numbers. So the rule is cut it in half. The next question is, when or where will your diameter be 6 millimeters again? Okay, you started off at 6. Now you get to the focus and you're 3. When will you be 6 again? And sometimes students think, well, let me just go back. And it's kind of like, I guess, but your beam is still going into the body, So think about the beam. Think about the beam going into the body. Reflections come back, that's true, but the beam continues. It continues to just into the body until eventually it fades out. So where would I be 6 again? And just look at the drawing. Notice how you start out wide and you slowly taper and get narrow and narrow and narrow. Now you're narrow and you're slowly getting wide and wide and wide and wide. So don't you think that if you're at 3 millimeters here at the focus and you slowly start getting wide, that you will eventually hit 6 millimeters again? Look at it getting wide. Okay. You will eventually hit 6 millimeters again, and then you'll blow past it because you continue to get wide. And the word for that is divergence. Divergence is when you spread out and you become wide. All right. So if I start out wide and get narrow, now I'm narrow and I start getting wide. And look at the pattern. Everything is really predictable when you look at it under those eyes. It took me 8 centimeters to be cut in half, wouldn't it take me 8 more centimeters to gain that back? Right? Like it took me 8 centimeters to be cut in half. So if I add another 8 and I start to spread out, I add that same distance again, then I should be back to that same width. Okay, so that's what you do. You add another 8. And in this case, you will be at 16 centimeters deep because this continues to go deeper into the body. This right here is 8 centimeters. What comes after it if you go deeper? 9, then 10, then 11. It doesn't start to count again. You know, you're still going deeper into the body. So the numbers continue to go big, to get bigger. So at 16 centimeters, that is when you are that width again of 6 millimeters. The rule basically is it's 2 times your near field. That's the rule. Because if you take your near field and multiply it by 2, you get 16. So that's the rule. All right, the focal zone, where does it start and where does it end? The focal zone stretches, if you can see here, it stretches part into the near field and part into the far field. Okay, half of it is in the near field. Half of it is in the far field. And I try to draw it, you know, to make it look like half and half. So where does it start and where does it end? For them to ask you this question, they have to tell you how big your focal zone is. So let's make it 4 centimeters big. So your focal zone is 4 centimeters big. Half of it is going to fall in the near field and half of it in the far field. What does that mean? 2 centimeters will be here and 2 centimeters will be here. That's half and half. 2 plus 2 is 4. Now the question is, where does it start, right? Like, okay, 2 centimeters, but what does this mean? Like, where does this all mean? It means that your focal zone, if I'm looking on this half, is going to start 2 centimeters to the left of my focus. So 2 centimeters to the left of this. So what's 2 centimeters to the left of that? It's going to be 6. Because I'm going shallow, right? 8 is here, then 7, then 6. 6 is 2 centimeters away from 8. So it starts at 6 centimeters. And then 2 centimeters from that, boom, my focus. And then you do the exact same thing for the other side. It starts 2 centimeters to the right of 8. And in this case, you're going deeper into the body. So 8, 9, 10. 10 is 2 centimeters away from 8. So it ends at 10 centimeters. And if you look at where it begins and you look at where it ends, it's a difference of 4. 6 plus 4 is 10. Mic drop. Right? So it all makes sense. You know, 6 plus 4 is 10. But just think of it, draw it out and think of it that way. 2 to the left, 2 to the right. But that's only when they tell you that the focal zone, you know, is 4 centimeters. Like if they were to say my focal zone is 6 centimeters, then I have to go 3 to the left and 3 to the right, because 3 plus 3 gives me 6. You know, so you have to look at what they're giving you, but just again, you cut it in half. Half on the left, half on the right. Okay. We're done with that. Now here's where chapter 8 and 9 kind of come together before I go into transducers. And I already say I'm going to be a little bit over my time, but it's all good. Chapter 8 and 9 start discussing a whole bunch of rules about the diameter size, the frequency, the propagation speed, and the thickness of the element. Okay, it gives you all these different things like, oh, what is the diameter of my element? What is the frequency of my element? What is the propagation speed in my element? What is the thickness of my element? And all of these things affect where your focus is. Okay, it affects where your focus is. So here's where you have to organize yourself in your mind. There are 2 kinds of physics going on right here. There is the single crystal physics, and then there is the multi-crystal physics. Essentially, they're the same physics, okay? Essentially, but the rules are like they're a little bit different. That's why I just say two kinds of physics. When we scan, we use multi-crystals. So for us, if you say high frequency, you're talking about shallow. That's for us. Anytime you pick up a transducer and you start scanning and you go high frequency, you are on shallow ground. But when you are in a single crystal transducer, high frequency means deep. And this is why I say two kinds of physics, okay? Again, it isn't really that, but sometimes it makes more sense to think of it that way so that you can separate them in your mind and treat them as such, all right? Luckily, I came up with a funny way to remember this, okay? Anytime you have a question and they bring up this jargon, crystal, PZT, element, or like the word diameter, but if they bring up the word diameter, they'll say the diameter of the crystal, PZT, or the element. If you have these terms, they're talking about this physics that I'm gonna go over right now. The phrase to remember is big, fast, deep for your focus. This is the phrase that explains that whole diameter, propagation speed, frequency, all that stuff. Is this phrase. Okay, if you can remember this phrase and what it means, it will get you through those questions. And what are the key elements when they're asking you about this? If they bring up crystal, PZT, element, or diameter, they bring that up. You bring this rule that I'm going to teach you. You bring this up to your mind, okay, and you apply that. So we're talking about the focus, where the focus is being placed. If it's big or if it's fast, your focus will be deep. And I'll draw it out, so don't worry. Now your job is to remember what falls under deep, what falls under fast. Okay, under deep is a big diameter crystal. So just a big diameter crystal. And they don't have to tell you, hey, listen, this crystal is big. They can just compare crystals. They can say crystal A is 4 millimeters, crystal B is 6 millimeters. This is the bigger one out of the two. Okay, so just that, whichever one's the biggest one. Okay, so under big falls a big diameter. Under big also falls a big frequency, which would be a high frequency. Okay, so if it's a high frequency, if they're comparing two crystals, one is a 10 megahertz, the other one is a 5 megahertz, the 10 megahertz is the big one. All right, so those are the two things that fall under big. Under fast, you have a high propagation speed in the crystal. And that's easy to remember because high propagation speed means fast, right? That's the definition of being a high propagation speed is being fast. So that one's easy to remember. But the other thing that falls under here is a crystal that is thin, okay, not thick. So here's where I bring up thickness, all right? Thick could easily fall here because thick, we could say is big, okay? So, you can make an argument and I would say, yeah, that's a valid argument. Thick could be confused with big. So why is it that that's not the case in my rule here? Well, because the book says so, that being thin is going to affect the propagation speed, and then the propagation speed affects the frequency, and then it places it deep. So nothing for you to worry about. Just remember this. So what's the way that I remember that thin is what I'm looking for and not thick? Well, if it's thin, I think about someone who is thin, someone who is skinny, and someone who is skinny can run fast. At least they can run faster than someone who is, thick bone, right? So that's how I remember that thin falls under fast. Okay, because I just think about a skinny person running fast. All right. So what does all of this mean? Now, you don't have to have all of these criteria. Like you don't have to have a big diameter, a high frequency, a high propagation speed, a thin crystal for it to be a deep focus. You don't have to have that. You can have just one. You can have a big diameter versus a small diameter. The big diameter will go deep. You can have a thick crystal versus a thin crystal. The thin crystal will go deep. So it's not you have to have all of these in order for this to be true. If you're asked a question on this, they'll just compare. They'll compare crystals. Like they can ask you which crystal will have the deepest focus. That could be the question. And let's just do two examples. In A, they can say you have a small diameter crystal with a high propagation speed. And in B, they say you have a high frequency with a thin crystal. And all you have to do is big, fast, deep. Right here. This combination will give me a deeper focus. Because if I pick A, yes, higher propagation speed will give me a deep focus, but this small diameter will cancel it out. Because what I'm looking for is a big diameter. Okay. So we just cancel it out. The job of the high propagation speed will get canceled out. All right, because the other one is not giving me a deep focus. Versus in B, both of them are heading for a deep focus. So that one is all in. Okay, so that's kind of like what they can ask you. All right, so what does this look like? It looks like this. I'll draw a crystal that's this big and a crystal that's this small. This crystal that is big, it has the same beam shape. It slowly tapers and then it gets wide. And in a small crystal, same thing. But because I'm small, my beam reaches that focus much quicker because I started out small. So it's going to get to that point much quicker and then it diverges. And what is all of this? Imaging depth. And that's what I say, deep focus. Look how deep my focus is right here versus this guy. This guy is 3 centimeters away. This guy is 7 centimeters deep. Okay, so that's what I mean by a deep focus. It's simply where your focus is placed. All right. Back when transducers only had one crystal and they only had one beam shape and one focal point, you couldn't move it. Your focus is where your focus is. So if what you were looking at happened to be right here, this is where the mass is, and you're using this transducer, sucks to be you. You're going to have to switch transducers to get one that has a focus around that area. Now we don't do that. Now we move our focal point. So we don't worry about that. But before, that wasn't the case. Before it was wherever your beam focuses, that's it. Nothing you can do about it. So that's why you have these rules that say, oh, if you have a big crystal, your focus could be deeper. If you have a small crystal, your focus could be shallow. So depending on what you're scanning, you may want a particular type of transducer. So let's say that you were scanning a thyroid with a single crystal transducer that we don't use anymore. But if you're scanning a thyroid, you know that thyroids are very superficial. So why would you pick a big diameter transducer? It's going to give you a deep focus. That's not going to work for the thyroid. In that case, you're going to pick a small diameter transducer to give you a shallow focus because the thyroid is shallow. So that's kind of the way that it works. Okay. And this affects lateral resolution, but we'll talk about that next class because that's lateral resolution.
Can I ask a quick question?
Yeah.
What if they give you like the big diameter but a low frequency? Would that not be related to this? Like low frequency, you would go deep.
Okay, yeah. So, right. So that's the other physics. So remember that I try to separate them as two different physics?
Yes.
Yeah, so this physics says that if you are high frequency, you go deep. And that's why when you're taking the exam, you need to, when you read the question, you need to look for these terms, crystal, PZT,
Okay.
element. Because
Okay.
the moment that the question brings up these terms, you apply this physics, quote unquote.
Okay, I think that's the chapter that was like disregard everything we talked about now.
Oh,
It was like confusing. Okay, thank you.
you're welcome. Now, how do they make it um, so that high frequency is shallow, right? Because we think about high frequency being shallow, and in this case, high frequency is supposed to be deep. So how do they make that work and convert it to being shallow? Well, what they do is, according to the book, what they do is they take a slab of PZT. So they take the element, the PZT element, and they chop it up into really tiny crystals, really, really tiny. But these are high frequency, but they chop it up into really, really tiny crystals. And when they do that, well, they made tiny crystals. And look at the rule. Big will get you deep. So the opposite of big will get you shallow. So they made them so tiny that even though they're high frequency, they're so tiny that they were forced to go shallow. It kind of like the shallow, the small crystal kind of took over the high frequency. They're still high frequency, but they made them so tiny that it completely countered the fact that it was going to go deep, and then it forced them to be shallow. Because you can take this rule, big, fast, deep, and just flip it and say small, slow, shallow, and then just flip everything else. Small diameter, low frequency, slow propagation speed, thick crystal, and then shallow focus. Okay. So they made these crystals so tiny that it just forced them to be shallow. That kind of like the balance, it wasn't a even balance where it was high frequency and like a decent crystal size. No, the whole tininess completely overpowered the high frequency and just forced it to be shallow. Because if you're small, you're supposed to be shallow. So that's how the book says that it kind of, fixed that. All right. Transducers, and I'm definitely over today. This is one of those days that I'm over my time, but no worries because transducers is actually quite simple. Chapter 12. So transducers. For transducers, what you need to remember are the names, the shapes, and a few little things about them. Okay, so we're going to start off with the mechanical transducer. Okay, the mechanical transducer, we don't use it. Okay, we don't use it. It's a single crystal transducer. It has one crystal. We're too ballers for that. We want hundreds of crystals. Okay, so this is a single crystal transducer. Um, it is completely mechanical. So there is nothing electric about it. It gets focused mechanically, and it is steered mechanically. And all that means is that the crystal inside this transducer has to physically move in order to create different scan lines. And that's how you make your image. Okay, so it has to physically move. That's mechanically. And then focused mechanically just means that we cannot move the focus the way that we do with electronic transducers. And then you can read about external focus versus internal focus for that. Single crystal, completely mechanical. Now, what is the shape of the image? The shape of the image is like this. It's a sector shape. So you can say sector shape, you can say pie shape, you can say pizza slice. Okay, so this is what the shape looks like, a sector shape. Okay, what happens if my crystal is damaged? Well, you only have one crystal, so your entire image is lost. Only one crystal. There's nothing else that can create an image. And then the other thing to remember is a little like advantage that this has. The mechanical transducers tend to use round crystals. And round crystals have an advantage of improving your elevational resolution. And we'll get into that on Monday. And this is all you need to know about mechanicals. And this is the same approach I'm going to take for all the transducers. Next is your annular. Your annular has a few crystals. So we're kind of improving. We went from one to a few. It's also half mechanical and half electronic. So it steers electronically, but it focuses mechanically. Okay, I'm not really sure you have to know that specifically, but it would be good to know that it's half and half, at least that. Okay, and notice that we're kind of like progressing. You know, we're progressing. We're going from single to few, from just mechanical to now mechanical and electronic. So we're slowly progressing. The image shape is the same. A sector shape, a pie shape, a pizza slice. All right, so it's the same shape. What if something is damaged? A crystal is damaged. Well, now it depends. It depends on which crystal. So the book draws a mechanical transducer or the crystal arrangement like this. It looks like a target sign. All right. And so let's pretend that these are three crystals. 1, 2, and 3 crystals. And we just spoke about this. Big crystals go deeper. Smaller crystals stay shallow. Number 1 is a small crystal. Number 3 is a big crystal. So the way that this works is this image is created, each part of this image is created by a specific crystal. The shallow will be my smallest crystal. My deepest will be my biggest crystal. And then in the middle will be my middle crystal. So this one image, and obviously we don't see it as like three separate parts, right? We will see it as one complete image. But just know that each part of the image is created by a particular crystal. So when we asked what happens if a crystal is damaged, this is why we say, well, which crystal is damaged? Because if crystal number 2 is damaged, then you lose that part of the image, because that part of the image is made by crystal number 2. If crystal number 1 is damaged, then you lose that part of the image, because that part of the image is created by crystal number 1. Okay, so that's the way it looks. So you'll see this drop off, this, horizontal drop off pretty much. That's how your image will look. You'll see tissue and then a complete drop off and then tissue again, assuming that, this is what happened. That's what you'll see. All right. What is are there any advantages to annular? Well, they're also round crystals. And round crystals, again, have that advantage that they increase your elevational resolution. But this one, annular, also increases your lateral resolution. Okay, and on Monday, you'll know why. The next one is your linear phased array, followed by your linear sequential array. Now we're getting into our world. Now these are the guys we use. Okay, now we're talking. So the linear phased array has many crystals, hundreds actually. And imagine fitting hundreds into that small transducer. That's why the crystals have to be so tiny. This one is completely electronic. The name of this transducer is the linear phased array. but they can call it the linear phased, and they can call it the sector. This is your cardiac transducer. This is the one that I use. And maybe, maybe one of you in this class is an echo tech, so maybe one of you, I'm just guessing, maybe one of you uses the cardiac. So this is your cardiac transducer. The thing about the linear phased array and the linear sequential array is that their names start and end the same way. The only difference is the middle. One says phased, the other one says sequential, okay? So if they ever are talking about this sector, it will say phased. That is the key. Okay, they will not say linear array and refer to this one. They have to say phased. So the moment you see phased, boom, is this one. And if they only say linear array, then it's this one. Okay, but I'll get to that. So what is the shape? Same thing, pie shape, sector shape. But now it makes a little bit more sense because this is the sector transducer and the shape is called a sector shape, so it makes a little bit more sense. What if a crystal is damaged? You cannot tell pretty much. You cannot tell. All you're going to see is a little bit of flickering of your image. Flickering. You'll see some little flickering of the image, like something is going on, like something static and flickering. You cannot really see like this drop off that you normally see in the other ones. And why is that? Is because all crystals are fired. Okay, one R, are fired at once. So all of these crystals are fired and they all start and originate from a single point. That is why it's so pointy. Okay, so all of these crystals are fired and they come together at one point and then they leave into the body. So imagine I love pizza. Okay, I love pizza. I used to be a vegan and pizza. Yeah, I'm about to vent right now. All right, get the tissues ready. So, so I love pizza. Then I went vegan and I didn't have any pizza or any cheese, obviously, because of the cheese. I didn't have any cheese for a year, and then I went into ultrasound school, and I was very, very busy being in ultrasound school, as you all may know. So I was really, really busy, and oh, there you go, Hector, vegan. um, so then I went into ultrasound school, and I was very, very busy. And I just needed quick things to eat sometimes. So I started eating pizza. And, then at that point, I just went vegetarian. Fun fact, though, for me, I didn't eat cheese for a year, just 1 year. But that 1 year, at least for me, was enough to change my taste buds for cheese. So when I have cheese now, I can only have it in small amounts because all I taste is salt. And I don't know if you've noticed this, but cheese is extremely salty. We just never notice it because we eat it so much. So, we become accustomed to it. But when I cut it for a year and then I had my first pizza, I was like, who the heck put so much salt in this? And it was just the cheese. So now when I have it, I just have it in small increments. And if I can avoid it, I just don't have it at all. So when I go to Chipotle, I don't get cheese. I'm like, nah, I'm good. If I go to Olive Garden and have a salad, I don't put cheese on my salad. I avoid it as much as I can because I don't really enjoy it as much anymore. But on pizza, I definitely like it. Why was I sharing that? Oh, because I'm a big marinara sauce guy. I'm definitely a marinara over pesto any day. Fight me if you want. Fight me if you want to say otherwise. So imagine that you're making a big, like 100 pounds of marinara sauce, and you're using hundreds and hundreds of tomatoes to make this marinara sauce. And in there, you throw one really rotten tomato. For whatever reason, it just kind of gets in there, right? You don't notice it, it just goes in there. One really, really rotten tomato. Do you think you're going to taste that in that big 100-pound of marinara sauce? You're not going to taste that. One tomato, okay, you're not going to taste that. So this is why you cannot notice that damaged crystal, because all of those crystals start out together and they leave together. So if one of them is lacking and broken or falling behind, the other ones make up for it. Okay, so if it all leaves in a group, one slows down, doesn't matter. Everything else still moves forward. Okay, so that's why that whole background of me being vegan is just to explain that. All right. Now, any advantages to this, as the other ones have? Not really. But once we get into completely electronic transducers, then we have all the electronic advantages to it. We have dynamic receive focusing. Okay, and then we have what is it called? I think it's called dynamic frequency tuning. Okay, so I won't explain these. Well, let me just take 5 seconds to explain them. Dynamic receive focusing is simply when the waves come back, which is why it's called receive. When the waves come back, they get focused again. So not only do they get focused when they go out, they get focused when they come back. That's dynamic receive focusing. Dynamic frequency tuning, it just means you have a lot of frequencies to choose from. So the machine tries to help you out and says, hey, listen, you have this big range of frequencies, right? Your wide bandwidth, right? You have this big range of frequencies. I'll do you a favor. When you create an image, you're going to have a shallow portion and you're going to have a deep portion. And your transducer can jump from 10 to 5, let's just say. So that shallow portion, I'm going to create it using your 10 megahertz because high frequency triumphs in the shallow. And this deep portion, I'm going to create it using your 5 megahertz. Because if you're trying to go deeper, you need to go a lower frequency. So it tries to use the best of both worlds for you, you know, because this is better than just using 5 all throughout, you know, because then that 5 will give you a good deep, but now you're using 5 for the shallow. And that's not really the best, right? So dynamic frequency tuning, you don't adjust this, you know, it's just something that's there to kind of, you know, to be smart, for the machine to be smart. So just little definitions. The linear sequential array, and this is where things just start repeating themselves. Many crystals, fully electronic. This one is called my linear array. So they can cut the sequential if they want to. They can just call it linear array. But remember, if it says phased, it's the other guy. Or they can also just call it the linear. That's what we call it when we scan. Hey, hand me the linear. Okay. The shape is a rectangle. That is the shape. What happens if a crystal is damaged? You're going to see a vertical drop off. So it'll look like this. Okay. These are the way that they're fired is in small groups. So like the crystals are bundled together and then they fired. And then the next bundle fires. The next bundle fires. And that's why you can kind of track it, you know, because now you're looking at separate little bundles rather than everything going out at once. So it's just a little vertical drop off. That's it. Okay. And that's really all you need to know about the linear sequential. Okay. And then everything carries over. This dynamic receive focusing, dynamic frequency tuning, all that stuff just carries over for anything that's fully electronic. So, but just be aware that that terminology exists. That's it. You're not really going to be asked about it. You just might see it pop up, you know, and it's if you are aware of it, it won't throw you off. You know, that's really it. All right, and then we just have a few more transducers and we're done. So bear with me, please. Then you have your curve linear. Okay, your curve linear, again, repeats itself. Many crystals, fully electronic. This one we just call our curve. That's the name that we give it. And this is for your abdomen. Oh, I forgot to tell you guys what the linear sequential is for. So the linear sequential is for your MSK, for your vascular, and for your small parts. And if you really want to get specific, even more than this, you would also use it for pediatrics. Because the small babies or small children, you will use a high frequency transducer, which is the linear sequential. All right, so this is what you use it for. I'll just put pediatrics here. Okay, so that's what you use it for. The curve, abdomen, OB, and what I don't like, GYN. I like OB, I don't like GYN. OB is fun to scan. I enjoy scanning OB when I was in school. I did not enjoy GYN. It's like, find me the ovary. Oh my God. Okay, so I guess it's gonna be here, and it's like the worst thing, trying to look for an ovary. All right. What is the shape of it? A curve. That's it. A little curve. If you have a damaged crystal, it's the same as it's the same as, yep, ovaries. There you go. If you have a damaged crystal, it's the same as the linear. You have a vertical drop off. Okay, you have a vertical drop off. Now this is really weird. It says that some, but not all, crystals are fired. I don't really think that you need to. I don't really think that you need to know this. That some, but not all, crystals are fired. But I'm just putting it out there. Okay. The big takeaway here is the name, what you use to scan, the image shape, and then that drop off if a crystal is damaged. That's the biggest takeaway here. The two more transducers, the tightly curve. Okay, there's something called a tightly curve, curvilinear, or the tightly curve. And it's essentially the same thing as the curvilinear, except that this is our transvaginal. Okay, transvaginal or endorectal, because you can actually use this for prostate exams. Okay, and what is the shape of it? It's kind of like the curve, the curve, but that curve is a lot more steep. So like this, and then it just fans out. All right, and that's all I know about it. I don't know about like if a crystal is damaged, and the book doesn't even cover tightly curve. But it's good for you to know that, because they can just ask you what they can say, what transducer creates this image. And if you look for that really steep curve, that is your tightly curve. Or what transducer can you use for transvaginals? Your tightly curve. All right. And then the last one. And then there was one. The last one, which is the easiest one, is your vector array. So the book doesn't say much about it. Many crystals, fully electronic. Okay, but it doesn't electronic. It doesn't go any much more detail. So what is it that they want you to know about this? They want you to know the image shape and where that image shape comes from. Okay, so let's start off where it comes from. It comes from your linear phased plus your linear array, which is basically your linear phased array and your linear sequential. Those two that sound very similar. And what is what are the shapes here? Well, the linear phase is your sector shape, which is this. And the linear sequential is your linear transducer, which is that rectangle, like this. So the vector array takes the flat top from your linear sequential and the spread out from your linear phased, and they call it the trapezoid, because it looks like a trapezoid, the shape of a trapezoid. That's basically what they want you to know. The name of it and what creates it. So they can just ask you a simple question. what transducer makes this image, and I'll show you an image, you know, of something being scanned, and look for that flat top. Nothing else is like, only one thing is flat top, which is the linear sequential. Okay, but the linear sequential is straight down. So nothing else looks like a flat top, and it spreads out. Okay, the curvilinear does spread out like this, but it doesn't have a flat top. It has a curved top. All right, so that's what you need to know about this. All right, that is it. Let me stop the recording.